Hi, everybody. Thank you for making it. So we're really happy to have Michael Reichle speaking today. So Michael is a PhD student at École Normale Supérieure, working with Brice Minot, and today he's going to be giving a talk on SSE and memory. Thanks, Michael.
Thanks, Sir, for the introduction. So yeah, as already said, I'll talk a bit about memory efficiency in Searchable encryption. Mainly are focusing on the result from crypto with Angèle Bossois, Raphaël Bos, Pierre Fouque, and Brice. Yeah, so about page efficiency. Okay. So yeah, just as a roadmap, initially I plan to talk a bit about searchable encryption, give a bit of a basic introduction. I'll probably go quite fast over that. Then about the problem statement and the solution, essentially. So problem being designing page efficient encryption schemes, and yeah, an allocation scheme that essentially allows to do that. So yeah, quick things about SSE. So when do you need it? Well, to outsource data on a cloud securely. For example, if you have sensitive data like a private email storage or hospital or company data that you want to outsource, and if it's sensitive, you need to encrypt it. So you of course need encryption for this, and in order to have encryption that you can, or in order to actually interact with the data, you kind of need searchable encryption, because if you don't, then you just have a blob of encrypted data you can't really interact with. And yeah, so searchable encryption essentially allows you to store encrypted data on the server and then perform search queries on the data. And yeah, essentially you want that the data is, or that you have privacy guarantees for your data and for subsequent search queries. There is multiple variants of this. For example, static SE has only search queries, and dynamic SE has search and update queries and different allowed queries, like you can think of SQL queries. But yeah, here I basically talk about static SE and very simple keyword queries, essentially. And yeah, and the adversary model is essentially that the server tries to learn information. So he still follows the protocol, but he tries to learn as much information about the data and the queries that the client makes as possible. So we really want to have a good privacy guarantee. The problem with having good privacy is that this kind of inherently incurs quite the overhead. While there are generic solutions like ORAM or for the encryption, they become quite expensive at a large scale, especially if you have a large amount of data. Generally, they scale with the number of identifiers they saw on the server. So in general, we allow for leakage, and the leakage that is kind of accepted as standard nowadays, I would suppose, is in setup the total number of elements in the database, so the total number of document identifiers, and then search, essentially repetition of queries and the IDs of document identifiers matching each query, or if you have response hiding schemes, then just the length of the answer, essentially. Yeah, and this essentially, like this leakage essentially allows to build very efficient schemes where we don't need high overhead by fairly generic solutions. And essentially the security model, so we want to prove essentially that the server learns nothing. So the server being the adversary learns nothing except the leakage. Yeah. And the thing that, so later on I'll talk about memory efficiency, and the thing that is important to keep in mind is that if we haven't created a keyword yet, we cannot leak anything about the keyword at that point of time. So later on we will make keyword queries, and yeah, and so for example, we cannot leak the length of uncreated keywords or something along those lines. And yeah, I guess already most people know here that there is no perfect solution for SSE yet, because generally you have a trade-off between functionality and security and efficiency also, I guess, in general. Anyways, there's still a bunch of this I don't know too much about, so I won't go into too much detail here, but there's a bunch of solutions, but yeah, they might not have the best security guarantees. possible. And yeah, I think I already mentioned this. So today I'm mainly focused on single keyword SSE. So you can search a single keyword, and then the document identifiers that match are retrieved. And I focus on it in the static case. So initially the database is fixed, and yeah, you can't really update the database. Yeah, and in that context, so essentially we have a reverse index. So the database is essentially a set of documents, each are identified by an identifier. And then in order to efficiently search matching documents for each keyword, we have a identifier list. And then whenever we query the keyword car, we want that the SSE scheme retrieves ID1 and ID3. So essentially for each keyword, here represented as objects, we want to retrieve a list that with all the matching identifiers essentially. Yeah, and so in general, how SSE works is you take this reverse index and then you encrypt it. So you generally encrypt the keyword, and basically the encryption of the keyword is then a search token. Not necessarily like a plain encryption. This could be more complex, or in general, this will oftentimes be a PRF. But yeah, essentially what the encryption of the token does, of the keyword does, is essentially generates a token. And then the token later on allows us to retrieve the encrypted version of the identifier list matching the keyword. And yeah, if you have any question, please feel free to ask anything on the fly. Yeah, so whenever we query a keyword now, essentially we recompute the token, so the search token, and then with that search token, the server can then retrieve the encrypted list, and then the client can retrieves the encrypted list, decrypts it, and has his documents. So I skipped a bunch of details about how the server actually retrieves the list in practice and how the token looks. So because of course the list has to be stored somehow in memory on the server. And the most naive solution for this would be to just pack every list after each other. So we just take the first list, store it into the memory, then the token kind of points to the beginning of the database. Then we take the second list, store it directly afterwards, and then the token points essentially to the after the first list, etc. But while this is fairly simple, this of course is not secure because we leak length of all keywords. Not necessarily all, but depending on the queries we do, we can kind of infer lengths of other keywords that we haven't queried yet, which by the security model shouldn't be possible. Yes, so essentially essentially the main problem is that the position of one list depends on another list, depends on the length of other lists. For example, if we query the yellow list, we know that the first keyword list is quite short because the yellow list is the second one, and there's only like a very small gap, which is encircled by blue lines, that can't really fit any other keyword than a very small one. So this is already not secure, but we can even give a distinguishing attack. So given two databases, we essentially now want to distinguish the databases just given essentially given this setup. So in the first database, essentially if we query these items, the server view essentially reveals that the items are fairly uniformly distributed. If we if the initial database 1 has only identifiers of size 1, and then database 2, there's one big keyword list with a bunch of identifiers, and in database 2 there's a huge gap, which is of the size of the red missing keyword. So here we can see that we can already simply distinguish two databases based on this. So while this is of course efficient, or this type of storage is efficient, this can't really be proven to be secure, because in fact it isn't. And so how most SSE schemes proceed is essentially they split each list into its identifiers, and then each identifier is stored in a random position in the memory. So yeah, this block, this gray box essentially depicts the memory, and then we just scatter around all the identifiers, and then the token essentially will later on allow us to retrieve the positions of all the identifiers, and then the server can still answer the queries even though they're not like adjacent to each other anymore. And actually, you can show that this is secure. I mean, I haven't gone into too much detail here, but yeah, you can actually see that, or you like with if you fill out a bunch of details, it's not that hard to see that this is secure, at least with the given leakage that standard leakage that I've mentioned before. But the main problem of this solution is that essentially for a list of length L, you need L uniformly random memory accesses. And in fact, while this might not seem in theory like a huge disadvantage, in practice actually turns out to be not that great, or actually quite terrible, because this is kind of the worst case for HDDs when it comes to read efficiency, for IO efficiency, because essentially HDDs thrive or are very, very good when it comes to reading continuous memory, but for random locations, for accessing random locations, it's quite bad actually. So this is not very fast. And then Cash and Desaro actually formalized this in 2014 already. And essentially they defined efficiency matrices or efficiency properties for SSE. The first one being locality. So that's the number of discontinuous memory accesses to answer a query. And the higher this number, the slower the access will be. And then read efficiency being the number of memory words that you need to access to answer a query in your SSE scheme divided by the number of memory words that you would need for a plain text answer with like a standard non-secure database. So yeah, and if both of these are low, then essentially you have very good memory efficiency, because then you kind of read close to the minimum amount essentially. And then lastly, also we never want to forget about storage efficiency, because later on we might store quite a lot of data on the server, and then we want to of course have the bare minimum of storage required to store our encrypted database. So yeah, and the maybe a bit unfortunate part about these three measures is, while they are predicting the efficiency of schemes, of SSE schemes on HDDs, on hard disk drives, if the SSE is secure, so it has standard leakage, then we can't actually have O of 1 in all three measures, which of course is kind of annoying for real-world databases, because then you can't really get like very good memory efficiency, which is also kind of the bottleneck of most SSE schemes, at least of like static keyword, single keyword SSE schemes. Nevertheless, there's been a lot of work actually on this type of problem, especially on building so like schemes that optimize the OO efficiency on HDDs. We call local SSE schemes, and especially Asharov et al. In stock 16 defined a bunch of schemes that actually come very close to constant efficiency, especially here the two-choice scheme with constant locality, constant storage efficiency, and constant read efficiency, and log and read efficiency, under a small condition that's not actually that restrictive in practice, or for example, Demetzis et al. Crypto 18, with a sublogarithmic scheme that is quite read efficient without any restriction on the list sizes. I think I'd like to note here that probably the two-choice scheme, so there's also a pad and split scheme where you essentially pad items to the next power of 2. The problem with that scheme is that then you pay a good amount in storage efficiency, which can be quite taxing if you actually have a lot of data. So, I mean, personally, I think that the two-choice scheme here is probably on a practical level the best bet, because usually your list sizes won't be too long, and the read efficiency in practice will still be quite well. So yeah, so in short, we have solutions, but they have, why they're quite good actually, they still have this minimal overhead, because you can't in fact get constant everywhere. And what we did in this article is essentially we looked at the alternative storage medium, and we defined page efficiency. And for this, I'd like to note that essentially there's two prevalent media for storage nowadays. So hard disk drives, which I talked about for now, and also solid state drives, so SSDs. And yeah, both of these actually have quite different functionality, or I mean, functionality is the same. You want to store data, persistent data, and you want to retrieve it, but the way they function is quite different. And yeah, also a small statistic. So nowadays, actually, SSDs become quite, become actually very, very important. And just because they're a lot faster than HDDs in practice, they become more and more prevalent. And I would guess in cloud storage, they also become are kind of like the go-to because of their efficiency. And then if we look at the performance criterions on HDDs, as I said, we have locality. So we want to optimize read efficiency. And the thing is that on SSDs, locality doesn't matter anymore. At least at least up to the page size. So I won't go. I will go into detail later. So essentially, what you really want for in practice for SSDs is to reduce the number of memory pages that you have to read. And what are memory pages? Well, essentially, the server memory is on an SSD is split into blocks. In practice, usually those blocks have all 4 kilobytes, and one of those blocks is 4 kilobytes, is essentially one page. And essentially, SSDs function in a way that whenever you access one page, the access is so if it doesn't really matter whether you access one item in the page or you access the entire page. The read or like the I/O throughput in both cases will be about the same. You always have to fetch the entire page essentially, and it doesn't also matter compared to HDDs whether if you fetch multiple pages, whether or not the pages are adjacent. Because essentially, like the maximum for I/O throughput is essentially fetching one page, and it's the same if you fetch, like it has the same speed if you fetch 2 pages that are adjacent, or 1 page or 2 pages that are completely random in memory. Or I mean, up to like a very, very tiny difference essentially. So yeah, and that's why essentially we define page efficiency as the number of pages accessed to answer a query, divided by the memory pages of a plaintext answer in the context of SSE. And yeah, like small last note on that. So essentially here we have a graph that depicts the throughput for given block sizes. So the green graph is HDDs. So if we read like the larger the block size, the more contiguous memory we read, and the faster actually the read will be. So the higher the throughput. But for SSDs, essentially the throughput has a maximum essentially at the page size limit. So essentially around 4 kilobyte, we won't have better throughput if we read more adjacent memory because we always fetch one page anyways. So I hope the motivation of page efficiency is clear. And now I go into essentially the solutions and more in detail about like the technical parts of the paper. And yeah, if there are any questions, feel free to ask. So yeah, as a small recap, so on HDDs, what matters is locality, read efficiency, and storage efficiency. And we know from Eurocrypt 14, from Cache anti-Zero, that you can actually have constant efficiency in all 3 measures. And now, of course, the question on SSDs is does the same thing hold? So do we have a lower bound for efficiency, or can we actually construct something that is optimal or as close to optimal as possible? And the answer is actually yes, at least in the static case. And if you think only about simple keyword queries. And yeah, I'll now go into essentially how you can actually get constant page and storage efficiency, and the technicalities behind that. So as a recap, so what we need to do is we need to, for storing our, so essentially for SSE, we need to store the list of identifiers that might have different sizes depending on the database that we actually want to store into the server memory. And we want to reduce the number of pages that we need in order to store them. And also we want to store like identifiers that match. So for example, the orange list, we want to store the orange list in as little different pages as possible to optimize page efficiency. And as a small note, without loss of general, and yeah, also we have a stash in our model where we can worst case allocate a few overflowing identifiers that we can't really fit anywhere else. And as a first note, without loss of generality, we can actually assume that the size of our lists is at most one page. And this is essentially because if we have one huge list that is longer than one page, we can just split it up into essentially lists that are exactly one page, and then one list that is at the limit, essentially that smaller than one page. And the main problem, the main technical difficulty is essentially storing these remaining lists that are smaller than one page, because the others we can actually just essentially store with the solution I sketched before randomly in memory, because if we put one page randomly in memory of identifiers, then if we read that page, we have perfect I/O efficiency anyways, because we just need to access one random page. So really what matters is the remaining lists that are at most one page. So how do we store them in practice? So these are all one page. Well, first we want to, of course, as already said, reduce the number of pages that we need to access to get one list. So this should be constant. And the number of pages that we need to store the encrypted database should also be linear in the number of pages that we would need for our plain text database. So the linear in essentially the sum of all list sizes divided by p. And for the security, as I mentioned before, we kind of don't want to leak any. So if we retrieve one list, we don't want to leak anything about other lists that we haven't accessed yet. And for this, we defined essentially data-dependent packing, which kind of ensures that if you retrieve one list, then essentially the pages that you need to access to retrieve the list only depend on the list identifier. So for example, the list identifier might be the keyword, and then essentially you can compute the pages that you retrieve as a function on essentially the keyword. And this ensures that the one list that you retrieve doesn't depend on the rest of the database. And actually, this is already, if you only want these properties, then actually it's not that trivial actually to come up with a solution. Because you need to store identifiers in as little pages as possible, but the pages can't really depend on others, so you can't really do any naive bin packing as you might want to do trivially or initially naively.
Sorry, Michel. Like just one question, just quick question. Maybe I missed maybe you mentioned it earlier in the intro. So how do you pick actually the size of the server memory? Like, is the server memory fixed as a parameter of your construction, or is it a function of the number of pairs?
So the server memory that you want in order to have good storage efficiency is essentially n pages, or like a constant factor times n pages, where n is essentially the size of the database if you wouldn't use encryption. So if you have n identifiers, then your server memory should be O of n, essentially. Does that answer the question, or is the question?
Yeah, so no, actually, like I was wondering, like let's say like in real world, like in real settings, for example, when you work on a server, it comes with a specific storage. Let's say like you have an SSD that has maybe like 10 gigabytes or 20 gigabytes or whatever, like some number of slots or number of pages that already come with your server. So here in the in the details that we are going through right now, are you assuming that the server memory or the number of pages, are they fixed independently, or is it like a parameter that it's independent of the size of the database? Or is, because when you mention the storage efficiency, it feels like it's a function of the size of the database, while,
yeah, it's a function
while the way how I would think about it is just like a constant, like it's just a parameter as well.
No, in this case, it's really a function of that depends on the database. So essentially, we want to recall that we are in the static setting, so we have a fixed database initially. So we really want to essentially use minimal storage for this database that we use in setup. So if the database has size n, then we want to use O of n server memory essentially. So we don't really assume that the server memory is a constant or anything. It needs to, of course, grow, or not necessarily, of course, but in our case, it needs to grow with the input database. And we don't really make use of. So if the server by any chance has more data, then we won't use up, or has more storage, then we won't use up more storage than this constant factor of the minimal size essentially.
Yep, makes sense. So, thank you. Yeah.
Okay. Yes. So even though there's like dots on the server memory, this is actually fixed size. Like it's fixed depending on the essentially the sum of the length of the lists. So, and now I go into details of how to actually do this allocation efficiently. So for this, we have our lists, and we want to allocate them in our server memory. So what we do is we choose for each keyword, for each list, we choose 2 random bins uniformly at random, and then we have the invariant that we want to allocate to each. Each list should be allocated in either one of the 2 pages that we chose at random or the stash. And the first thing to note, if we do that, then we trivially get data independence, because now essentially the 2 randomly chosen bins, they could, for example, be a hash function on the identifier, and then the 2 bins only depend on the identifier of one list. It doesn't really matter like whether or not you store other identifiers in the buckets. You always know that you have to retrieve to access 2 buckets in order to retrieve your list. Yes, so you do this, and then you can just try to, no matter how, you can try to allocate your items. So for example, putting everything, every list into the leftmost bucket, onto the leftmost page. And if you do that, what you get is a bunch of overflowing pages actually, and then you can put the overflow into the stash. So while this, of course, already works, this is essentially kind of one choice allocation, and you get a worst case bucket load of log n, but you have a bunch of other overflowing buckets also. So in total, your stash size might be actually quite large. So this, of course, is not complete yet as a solution. It is kind of the initial point of the algorithm, though. So and now that we've allocated our items, we can actually optimize this solution. So the first trivial optimization is, if we look at the gray list, we can see that it has 2 choices, and the other choice is not full yet. So essentially, we can also, because there's still space in the green bucket, we can put a bunch of items into the into the green bucket essentially. So we can do this twice because there's space for 2 identifiers. So we already optimized the space a bit, and we can also do the same thing for the orange list. So if we follow the path, like the path from this page to the other choice for the orange list, then we can do the same allocation. And now we already reduced the overflow by quite a bit. But in fact, this can even be further optimized because if you look at the violet items, then you can see that there's an alternative bucket choice for the violet items that is not full yet. And then on the other hand, the orange item wants to be like one of the orange items on the left could be allocated to the bin that is shared with the violet items. So in fact, we can just find paths from overflowing bins to underflowing bins, and then we can just push the items along the path and reduce the storage by this. So essentially the orange item will then be allocated to the violet/orange bin, and the violet item will just be pushed to its alternative allocation. And this has been a bit informal. So how can you actually formally compute this? Well, what you do is for each page, you essentially take you interpret each page as a vertex in a graph, and then for each identifier per list, so for each list item, we take one edge between both vertices. So for each page, so each list has 2 page choices. So for each identifier in a list, we draw one edge between both bin choices, essentially, so between both vertices. So these are essentially the paths that essentially already that I drew in the picture, just not with the multiplicity. So for example, we would have, instead of having like this one orange edge, we would have 5 orange edges. Yes. And then what we want to do in this graph is we want to find a maximal set of disjoint paths from overflow pages to underflow pages. This is essentially what we just did. So we try to find paths from overflow to underflow full pages, and then we can just push items along the path, and then we optimize for each path, we optimize the solution by 1. So we reduce the total overflow by 1. And this is essentially exactly a max flow algorithm. So if we just we just build a graph, we run a max flow algorithm, and then we get a fairly good solution. So in summary, what do we do? For Tetris, we essentially choose 2 uniformly. Sorry?
Sorry, I think there's a question.
Yes.
Yeah, I had one question. So I was wondering that how much control as a client do we really have over how server really allocates client data in its memory? Can we really say that, okay, store my data in X, Y, and Z pages?
I mean, we kind of assume that the server is honest but curious, right? So, and the server doesn't really gain anything from not allocating anything efficiently, right? Because the server also, I mean, if you query something, you use the server, and the server, like you query the server, right? And then this server actually pays, like the less efficient the answer is, the worse for the server also, right? Because the server also pays in resources. So if the server doesn't really follow the protocol, then, I mean, he doesn't really gain any more information about this. There's no information gain. And in practice, so this is what Reichle did. In practice, you can also just build SSE schemes that go very deep into essentially this allocation mechanism and optimize actually that. So if you say that the algorithm should store something in one page, then you can actually enforce the operating system to do so. I'm not very knowledgeable about this because Reichle did this, but yeah, in fact, you can actually do this. This is a bit operating system dependent, but yeah.
Right. So as a client, I should have knowledge about how much space does actually the server has and how it's allocating its memory. Right, because here if we are choosing pages randomly, I should be able to dictate that, right? Like that the first list should go in this first and fifth page of your SSD.
Sorry, can you come again? I didn't quite get the last part.
So for example, in this example that we have here on this slide, for storing X1 as a client, I'm selecting 2 pages of server's SSD randomly, right? And then I really want server to store this X1 into these 2 pages that I've chosen randomly. So I was just wondering that how much control do I have?
Yeah, I mean,
the server possibly will be storing others' data as well, right?
Yeah, I mean, during setup, what you do is you just essentially you encrypt your pages, and then the server essentially gets a set of encrypted pages, and then the server has to store those according to what you defined, right? Later on he will, like, the pages are essentially behind a hash table in practice, and then in order to actually retrieve your identifiers, or like the 2 pages, the server has to store them at like certain locations in memory, right?
Okay.
Like using a hash table essentially. And if the hash table then later on is optimized such that it stores like 1 item of size P in 1 memory page, then you actually also optimize the memory efficiency. That's kind of what you have to do in order to implement this, I guess.
Okay, thank you.
Okay, perfect. So going a bit over the summary again. We choose 2 random pages for each list. Then we put each list into 2 pages arbitrarily, and then we optimize the solution by computing a max flow over the graph that I just mentioned before. Then we have a set of paths that are disjoint. Then we move items along the paths, and in the end, items that still overflow go to the stash. And this essentially is a graph optimization problem. So what you want to do is you want to minimize the stash. So you want to minimize the stash under the constraint that items are assigned somewhere, and that no page overflows. And worst case, you just assign items to the stash. And you can actually show that Tetris is optimal with regards to this optimization problem, meaning that whatever starting configuration you have, so however you chose initially to allocate your lists, if you run the max flow algorithm, then in the end, you get a optimal stash size with regards to like your 2 bin choices, essentially. Yes, so Tetris is optimal, but of course, we don't have an upper bound yet. So even though it's optimal, worst case, we might still have a huge stash. And so we still need to analyze the stash size. And what you can show, so for the parameters n and s, so n being the number of pages in the database, so essentially the number, like the total sum of all the of the number of all identifiers divided by p, and then s is the number of pages in the stash. And essentially what we do then is we pick m as 2 plus epsilon times n. So essentially m being the server storage that the server then later on needs in order to store the encrypted database. So on the server, we allocate 2 plus epsilon times n pages, and epsilon can be any constant. So I think in practice, we chose 0.1 for our experiment. So around 2.1, you can think of it like a bit more than 2 storage efficiency. Essentially, you get around 2 plus a bit storage efficiency. So if you pick m this way, then you get as the central theorem, you get that for any set of lists, so independent, so the list distribution really doesn't matter here. You can have like a lot of lists with only 1 identifier, lists with random identifiers, whatever. For any set of lists, you get that the probability of that the minimal stash size is bigger than s is O of n to the power of minus s over 2. So in practice, so in theory, you can just choose the stash size. So s being a function of the security parameter and the number of pages that you need. And if you choose omega of log secpar, the security parameter, so omega of log lambda divided by log n, then you get that the probability of failure is negligible. So in practice, you need this stash size in order to allocate everything, like all your identifier lists, into 2 plus epsilon times n pages. And then later on you store the stash on the client side. So this is important. And here it's important that to note that actually the stash size doesn't grow with the size of the database. Actually, the more data you have, the better essentially your probability averages out, and the smaller your stash size actually will be. And it doesn't grow in the size of the database. So your client actually can have very small client storage, so a few pages essentially, and still outsource a huge amount of data essentially, with good memory efficiency. So a few small remarks about the proof. As a setup, what we need to define is L to be a set of lists of sizes. So L is essentially the abstract view of the identifier list that we had before. And essentially for each list in the multiset, we have the size of the list. And then for this, so this is essentially what we start with. We want to allocate like a list distribution that kind of is arbitrary. So L is kind of this arbitrary list distribution. Still with the size n times p. So essentially we need n times p. So we need n pages. So in total n times p identifiers. And M is a multiset with only full pages. So each list has p identifiers. And we also want that the sum is the same. So that essentially the setup leakage is the same for both list distributions. Or the database size essentially is the same. And then essentially the central statement of the proof is that, so this is a bit simplified. I might talk a bit more about this in detail later on, depending on the time, but essentially simplified, you get that the probability that the minimal stash size is bigger than S. So the probability that your stash overflows with the initial list distribution L, so an arbitrary list distribution, is smaller or equal to, or so it's upper bounded by the probability that the minimal stash size overflows, or is bigger than S, so that the stash overflows, given the list distribution M. So what this means in practice is that this is the worst case. So the worst case for this allocation problem is essentially if you have a lot of lists with all full P identifiers that all fit exactly into one page. And then you have, and then you want to allocate those into pages of size P. So essentially each of those pages has size for one list exactly. So this is the worst case. And in fact, if we reduce, so this is the situation with M, with our multiset M, and if we scale this by a factor P, and we have like items of size 1 and bins that each can store up to one identifier, and for each of those we have for each bin ball we have essentially 2 choices, and we can optimize the solution. Then this is essentially exactly cuckoo hashing. So essentially what we built is a weighted version of cuckoo hashing, and then we can actually reduce the stash analyzers of this weighted version to the standard cuckoo hashing stash analyzers. So the bound is essentially coming from the bounds for standard cuckoo hashing. Yes, so far so good for the proof. And yeah, I don't know how much time I have because I forgot my timer, but this is one of the last slides. So I just quickly go over how Tethys works. Like if we use this allocation scheme, so we have our client wants to, so initially we run the Tethys allocation. We, yeah, I already put this. So it's initially we run the Tethys allocation. Then we get this hash table that maps essentially, yeah, memory locations to pages, and then the pages are essentially filled with our list identifiers according to Tethys. And now if we query a keyword, we essentially generate our search token by kind of encrypting the keyword. Then we send this to the server, and then based on the search token, the server can then recompute the two bin locations. And based on these bin locations, the server can then retrieve the 2 pages necessary, where essentially our items are stored. And if we decrypt them, then we can retrieve the matching identifiers essentially. And efficiency-wise, we have good page efficiency. So we have, for each list, we need to access 2 pages. And because later on, like for now, I simplified everything. So every list has a most size 1, but in practice has a most size p. Practice, of course, this is not necessarily the case. So we need to also retrieve the number of sublists essentially for each list. And this essentially is the +1. So essentially we have page efficiency 3 for Tethys. Storage efficiency is 2 plus epsilon, because we need that many pages in order for Tethys to work with negligible failure probability. And the client storage is, yeah, the size of the stash. So yeah, a few pages in practice. Yes, also a small note here. So you might try to optimize this. So here we have, for accessing one list, we have to retrieve 2 pages. And you might think of optimizing this and just decrypting them on the server and then only sending back the matching identifiers. Because then you save a bit in communication. The problem with that is that then you leak information, or you might potentially leak information about other lists that you haven't queried yet. So here, for example, you might leak information about divided lists or the gray list, and like how essentially your lists are distributed. So you can't really optimize it in that way. And maybe there's possibilities, but at least not naively. So yeah, that's how Tethys works. And then yeah, this is just like all the measurements in theory compared to a bunch of schemes, mainly local schemes if you interpret them as page efficient schemes. So yeah, you have constant page efficiency, constant storage efficiency, and yeah, a fairly small client storage that only scales with the security parameter. And in practice, if we Reichle actually simulated this with so first of all, he implemented Tethys, optimized by page efficiency, optimized for essentially for essentially optimized in such a way that the accessed pages from the operating system actually match the number of pages accessed in theory. And yeah, this is depicted here in the graph by Tethys real. And then we simulated essentially a bunch of other schemes. So their throughput, their page efficiency, and their storage efficiency, and also their read efficiency. And yeah, essentially you can see that Tethys actually comes quite close to a plain text database in the efficiency measures, and it's the only one that kind of comes close in all measures that we care about. But yeah, the last thing to note maybe is that, yeah, this is still only static, and this is only for single keyword, for like simple keyword searches. But yeah, there's probably a lot of things to be done with page efficiency, I guess. Yeah, and I have no idea about timing, But with that, I think I would be finished and I'd be ready to answer questions.
Great. Thank you. Let's thank the speaker. Yeah, so we have 5 minutes for questions. So I guess I have a question, which is, so yeah, it's a really nice scheme. And as you said, it's mostly designed for static data. And it seems like extending it to dynamic seems really non-trivial. It almost, you know, I mean, without just downloading the data and recomputing everything from scratch, it's not obvious at all, like how to do it another way. So is there some sense that like these techniques are basically, or this approach is limited to static, or is there some hope that they can still work in the dynamic case without doing the trivial rebuild?
So we actually did a bunch of, like following this paper, we actually did a bunch of research on this. And I don't know how much I should say, maybe Brice can dive in, but essentially, yeah, this approach is fairly limited because you need to essentially obliviously compute a max flow algorithm if you want to update stuff, right? Because with a max flow, you can optimize your allocation. The problem with that is that max flows are fairly expensive. Yeah, generally, I guess the standard solution for this is oblivious sorts. And you really don't want to run one oblivious sort for each item that you insert in the database. I mean, I haven't checked details, but probably like if you do something along those lines, like for each added identifier, you run one oblivious sort on the entire database, then yes, this is dynamic, but it's very horrible concerning efficiency. But yeah, there's some hope if you change up the algorithms a bit. But yeah, this is still in the work, and yeah, it's heavily non-trivial to actually make this dynamic the way it is.
Okay, great. Any other questions?
So I actually have another question. So it's a really interesting scheme, and I really like the great presentation. It's really nice. Thanks, Michel. So one question I had, like, you know, it was just really interesting to, maybe you already talked about this. So when you were comparing to locality at the beginning, in the sense that you had, you know, there was this very nice result by Stefano and David, that you cannot achieve the best of all of the three words. And you said, no, we can achieve it in the page efficiency setting. Yeah. So, but it seems like that you have included another parameter, or at least for me, it seems like another dimension, which is the client-side storage, which is here something that it wasn't accounted for in the locality, at least model, is just that you cannot achieve the best of three words. But it seems like for your setting as well, you cannot achieve the best of three words if we account for client storage as well, because client storage is not constant. So is it like something that you have accounted for when you were working on this paper, or you wanted just to dismiss client storage? Because it wasn't kind of like fair when you compare locality to page efficiency in some sense.
Yeah, okay. I mean, in some sense, there's also, I mean, yes, there might be a solution with that is optimal with locality, with a bit of stash, like if you allow for a stash, but we know of nothing. So you essentially in the case of locality, we don't actually know, or I don't know of a way of actually making use of a stash. Whereas, yeah, I mean, in this case, we make use of a stash. So yeah, maybe there's a lower bound that holds with respect to the stash. So yeah, if you don't allow a client stash, then of course you can't run Tetris, at least not with negligible failure probability. Or you have to outsource your stash on the data on the server, and then you kind of pay the. It's not a huge cost, but you always read the pages. So in theory, it's not constant anymore. So yeah, I mean, it's not clear. I mean, I guess personally, I would suspect there's also some. I mean, at least in something like a balls and bin model, that there should be something like a lower bound if you don't allow for a stash. But Yeah, I guess, I mean, in practice, I think a stash is actually not that bad. I mean, it kind of depends really on the setting, but in general, I mean, the stash is really just a few pages, and in general, most clients should, I guess, have at least a few pages to spare, unless maybe smartphones, but maybe then you can run kind of an intermediate or something along those lines. So yeah, I guess that's kind of the answer I have. Yeah, it's maybe not, I mean, yeah, concerning the stash size, it's not optimal yet, but like for practically relevant efficiency, I would say that it's still like fairly close to being optimal, at least in the simplified setting.
Just to add a little bit to what Michael said, I completely agree with you. Actually, I thought about it as well, about trying to get a scheme that also has constant client storage, and I didn't find it. I didn't find a solution, and I don't know if there is a lower bound of if it's possible or not.
Yeah, that's really interesting, because it seems like hard. Like when I'm thinking also about it, it seems really hard to do it without extra storage or without extra communication complexity. So there might be, so this is actually why I was asking the question, is that like maybe there is this client's storage, which is the third dimension actually of this problem, which is actually you cannot achieve the best of the three words, which is kind of like very like by analogy, like similar to the locality problem as well, where you cannot achieve also the best of three words. Anyway, it's like
I agree. But like Michael said, in practice, it's a few pages. So it depends on the context. It's not too bad, but yeah.
Yeah, it's definitely an interesting question for theory, I would say. And also thinking about dynamic schemes, like, can you actually get this efficiency dynamically, stuff like this? So there's still a good amount of interesting open problems, I guess.
Thank you.
Okay, great. We don't have another question. All right, let's thank Michael for the great talk. Thank you. And yeah, we'll see everybody again at the next talk. All right. Bye.
Bye, everyone. Thank you.
Thanks.